Okay, hi everybody. There's nobody at home at the moment, so I hope that home is hearing, but home is only hearing retrospectively. Um, let's just hope that it's okay. The previous lectures were wonderful and never fumbling a recording, so I hope you're here on YouTube as well. If so, then something good happened. Welcome to the last week, week 13. I think you know me, so no need for introduction because I've been bugging you with emails the whole semester. And now you get 3 hours with me, 2 hours today and an hour tomorrow, dealing with machine learning, Unit 8. And that's the end of a course which I think most of you will agree with me has been very long and hard. I hope you learned something. I'm not going to ask just right now because I'll get a tomato thrown at me. Somebody joined at home. Can you hear at home? Just can the person at home let me know that audio is working and all that? If you can just put that in the chat, that would be great. Well, anyway, so project number 3 was released today. And before I even go to the content, we'll just look at it quickly. As with the other projects, there's an explainer video for the project. Just to be clear, you've got part 1, part 2, and in each part you have option A, option B. So you can choose A, B, B, A, B, B. Okay, like mix and match. The slightly more, I can say, straightforward option is 1A for part 1, and that's been like that in previous years as well. As with other projects, there's nothing stopping you from looking at what others did in previous years as well, but we make sure that what you're doing is different and is on top of that. So this type of work that you're going to do in here associated with Unit 7 with data analysis is what many of our graduates find themselves doing in entry-level jobs, but then throughout afterwards. So being able to analyze, wrangle data sets, etc., that's what you're doing. We're not asking for a full scientific report. It's more that you get to carry out each of the tasks, and our importance in this course is to have the programming perspective covered. You'll have other courses where actually the content and the statistics are the focus. If you choose option B, then the sky's the limit. Go ahead and make a very nice video. The hardship that students that have attempted to do such a thing in previous years have found was aligning latitude, longitude coordinates with a map and stuff like that. But you guys understand linear transformations, etc. You don't need to worry about the curvature of the Earth. This is within Melbourne, even though Melbourne is way too big. Okay, but it's about making a nice movie, creating code for making a nice movie. So that's the other option. So that involves some data analysis also, obviously. Now, and this project 3, is lighter than the other 2 projects, just to be clear. When you go to part 2, so this is a completely different story. So we have 2 very classic data sets in the world of machine learning. We'll speak about them today. The most popular, the MNIST digits data set. And a friend is the fashion MNIST, much less popular. What's nice about the 2 is that they have the same structure. 60,000 training images, 10,000 test images. Each image is 28 by 28 pixels, monochrome. There are 10 labels, the digits 0 through 9, or shirt, blouse, shorts, etc. The practical this week, this last practical, I recommend going to this last practical, especially because practicals are not recorded. The practical covers the fashion MNIST dataset and also some logistic regression-based gradient descent. If somehow you miss the practical this week, you can go to Blackboard, not to YouTube, Blackboard, and then see the recording of the practical from last year, that last practical, okay? But better to get it live from the tutors. So again, option 2A is somewhat easier. It has these 4 tasks, and each of these tasks you're actually doing stuff that we'll cover in the lecture today, but slightly different, and applying it to the MNIST dataset. In this case, you're not predicting what is the digit, but you're rather predicting if the digit is straight up or 90 degrees like this, or 180 degrees or 270 degrees, etc. Okay, so you assume it's one of these 4 orientations. But to do that, you also prepare the dataset. So you do the rotations yourself, and you could work out how to do that in one of several ways. Okay, so that's this task. The other option is to do everything that's the focus of tomorrow's lecture, and that's to use actually a very strong algorithm called random forest. So tomorrow we'll speak about this, the last lecture. Tomorrow we'll speak about decision trees and random forests. Okay, and unlike gradient-based deep learning, which you'll understand what is today, or what has become the most popular tool in the sense of machine learning, random forest is a different type of algorithm. Programmatically, it's a bit more difficult because it requires some recursions, etc. And that's why we thought it's useful in the course. Okay, so that's why you do an option 2B. I think that 2B is more difficult than 2A, but difficulty is subjective. And anyway, do what works for you. We'll try to have projects too marked within 10 days from now. So that can also give you an indication of really how much effort you need and want to put in to finish project 3. I know this is exam period in other courses. You have exams, right? Okay, good. Okay, any questions, thoughts? Tomatoes, tools you want to throw at me? No? Okay, I got one. Let's hope it was a tomato. All right, so let's get to now unit 8, and that's a taste of machine learning. So at UQ, you have options for doing many machine learning courses, and this is not a machine learning course. This is a programming course where you're touching things from the world of mathematics, namely analysis and learning and simulation, and that's pretty much what you did. So now, in terms of machine learning, I hope that you come out of this course and you can do things quite quickly. So when you do another machine learning course, even though you might use Python there and not Julia, then you can adapt quickly. You can script easy and things like that, because the projects that you've done here are beyond the basic machine learning scripting. So machine learning is often what you do as a machine learning engineer, as a machine learning professional, is carry out kind of use scripts. It's not necessarily create these more structured programs, and that's what you guys have done during the course. So just so you know, in terms of course the UQ, so Stat 3007 is a deep learning course, and it's recommended for industry, etc. Stat 3006, this is a course that's about statistical learning, much more mathematical. Hilbert spaces are used, things like that, etc. Analysis of machine learning, or the way that statisticians sometimes call it, is statistical learning. And you got a 4th level course if you're doing honors sometime in the future, Stat 4401. There's also a great computer science course, Comp 4702, which is a much more, let me say, pedestrian machine learning course. So it's here's an algorithm, here's how you implement it. Here's an algorithm, here's how you implement it. But you really learn the basics of machine learning. And there's jobs, there are job opportunities in the world of machine learning. Often a data scientist, so I know people that have graduated from this course and work in industry in their first year of industry, etc. They do data science, they do unit 7 type of stuff most of the time, analysis of data sets, but from time to time they also slap on a machine learning algorithm. So machine learning, what is it about? I actually think you probably know, but let's say it anyway, and stop me, of course, for questions if you have any. So the main story is to do statistics, but pretty much at scale, where you have your real world that actually generates some data for you. And this data often has some patterns. Okay, so, and patterns are, I'm lifting this thing up and everybody knows it's a bottle. That is one type of pattern, but also patterns can be much more complex, not in the realm of things that we can do as humans. Okay, so if you look at these patterns, we might view them very simply as this matrix of table that has the X and the Y. Okay, where every row of this large matrix is going to be one sample. So let's say that I want to know the difference between a bottle and a phone, then I'll have many rows that are X and many rows that are phone and many rows that are bottle, and that will be my X. How does X fit in a row? Well, I'll take an image and I'll vectorize it into a row, for example. That's one way. Okay, and the columns, so you can call the rows observations, just like in your basic stats course, which all of you have done in one way or another. Okay, observations, all right? And the columns of this thing, you can call them features or coordinates, okay? So for example, in the data sets that you're using for the digits, there are 28 by 28 pixels, monochrome, so not color, so you don't have another layer of RGB or something like that. 28 by 28 is 784. So you have 784 rows. We'll see this shortly. And then you have this other column that's thinner, and that's Y. So X predicts Y. You have seen that paradigm in statistics before. Y is going to be, say, 1 for a bottle, 0 for a phone. 1 for a bottle, 0 for a phone. That's one example. Okay. So the world generates this data. And our assumptions are that the data that we've seen before is also going to be similar to the data tomorrow, because bottles tomorrow will not look completely different than this, and neither will phones. Okay. But of course, people have to work for this. So that's a whole story of its own. And then you stick this in a learning algorithm. So what a learning algorithm does, it takes this data, crunches it. We're going to run some learning algorithms today, and it gives you a model. And the model is something where you can stick one example of an unseen bottle that has not been seen before, okay, or an unseen phone, okay? And the model will give you a Y hat, a predictor, okay? That's a story, right? So they're kind of two tasks, or maybe we shouldn't call them tasks. There are two activities, sorry, I'm a bit under the weather. Two activities. One activity is the learning activity, creation of the model. One activity is the application or the production time of the model, using the model, okay? So when you use, for those of you that have, well, voice systems like in iOS, it's Siri. When you speak to it, you're doing this thing on the right, okay? The thing on the left happens offline, typically. So that's a normal paradigm. Of course, there are more complex systems that learn continuously as you use them, etc. Siri is certainly not one of them, the iOS Siri, okay? So this whole paradigm is called supervised learning in machine learning, and it's called supervised. Well, to see why it's supervised, let's actually compare it to another paradigm, which is called unsupervised learning. So in the unsupervised learning, we don't have labels. We don't have the Y column. We don't have, is it a bottle or is it a phone? We just have pictures of things, okay? So think that you're stranded on an island from age 1. Somehow you have some food in the refrigerator and you grow up and there are no predator animals, etc. And you're unsupervised and you grow and you see a bunch of bottles that kind of washed up over there, unfortunately, and also a couple of phones that fell somehow from the sky, okay? And after a while, you'd know that this is Gigi and this is Lala, right? So you do unsupervised learning that this is different than that, all right? So that's unsupervised learning. That's a different type of problem. Now, the task that we spoke about here in supervised learning was the classification task, classified if it's this or it's it. You can also have a different task. You can have a regression task. A regression task, kind of like linear regression, but the word when people say regression task is what is the angle of the bottle? Okay, so a continuous variable, for example, all right? Is your project, the machine learning part there, option 2A, is that classification or regression? It sounds like regression because we want the angle, right? But we're actually asking you to treat it as a classification test because it's going to be 0, 90, 180, 270. Okay? Yeah.
So what's the difference between supervised and unsupervised?
Right. Okay. So well, I'm just getting to supervised. Good question. So I've just moved for a second back to supervised to also make the dichotomy between the two main tasks, classification and regression. Okay. Now, when we get here to the unsupervised, let's see what we can do, what kind of tasks we can do. So there are different tasks. One very important task is called clustering. And that's, imagine you're on that island, and after a while you decide to clean up your island, okay? So you've got your bottles and you've got your phones and you put them aside, all right? So that's clustering. So how does clustering work? You take all of your input data, X, and you stick it in a clustering algorithm. Okay, again, each row of this X is one set of inputs. Now, by the way, in machine learning, unlike classical statistics, you've done some classical stats course, linear regression, stuff like that. You don't have 2 or 3 or 7 variables. You know, you have variables in the hundreds or in the thousands or more, right? So the number of columns is, you know, it can be the number of pixels or it can be text, etc. So a clustering algorithm would take your data and would separate it into different clusters. We'll run this today and we'll see examples. Okay, so you put, you know, the bottles, the phones, maybe you have more than 2 options. Of course, anything that has 2 is called binary. And when you have more than 2 in the lingo of machine learning, it's called multi-class. Okay, that's just the language used. Now, it will also give you a clustering algorithm, where the clustering algorithm is, again, sorry, the clustering model. Now, I made this mistake. I called the model algorithm, but in machine learning, there is the learning algorithm, but the output of the learning algorithm, the model, is sometimes called an algorithm also. You know, when politicians speak about the algorithm of Facebook or whatever, they don't really understand, obviously. I mean, even when they speak about simpler things, politicians typically don't understand. But anyway, this is the algorithm. Okay, the model is the algorithm, is what you can use. And then you could use that algorithm on new things, and you could say, hey, here are two things. Are they the same or not? So that is one example of an unsupervised task. A couple of years ago in a consulting project, I used this for helping a company that had customer data. Okay, so customer data, your input data X would have, you know, each row is a customer. You know, so it had several thousand customers, and each column was an attribute of the customer: the country, the size of the customer, how many purchases, etc. And it's very natural for a company that's doing marketing to cluster their customers, not to treat them as 3,000 individual customers, but to treat them as K, you know, K is 7 or 8 different customers, and each one was a persona, and then they can kind of tailor their marketing for each customer type. Okay, so they know what are typical personas. So that's clustering, but there are many more constructive uses beyond marketing. A different type of task in the world of machine learning is data reduction. So what does data reduction do? Again, you take your input data, exactly like here. You stick it through the machine learning algorithm with data reduction. Spoiler, PCA, you've heard of PCA, principal component analysis. That's the most basic example of this. Okay, so we'll see an algorithm of each. Okay, so data reduction. And what you're doing is you're actually lowering the dimension. So if you had, say, 784 features here, you only have 20 features, for example. So you've taken something that's in a high dimensional space, because, I mean, we can only visualize 2 or 3 dimensionals at a point, right? I mean, unless we visualize the image, and you put it in a lower dimension. Okay, why would you do this? Well, we'll take you back after we get to that part. And for example, task this is task in the sense of homework task 2.4a. We could speak about this for a minute. So that's, for example, one thing you might do with this. Okay, so in a form, compress the data. Okay, and then your features, your columns here, are not the same meaningful features they were here. There's something else. In the world of PCA, it's called principal components. We'll speak about it briefly. Yeah.
With the clustering, do we get to choose how many clusters there are?
Yeah.
Once.
Yeah, great question. So there is a word in the world of machine learning that's called a hyperparameter. Okay, well, first of all, I say parameter. What is a parameter? The word parameter in general means something that you learn. Okay, so a parameter is something that lives in the model. Okay, so that's something that's an output that you learn. A hyperparameter is something that a priori outside of the learning process, you go and you say, okay, I'll tweak it and I'll set that to be 7 or 10. So for example, in clustering, the number of clusters is a hyperparameter. And then you get to a whole different area, which is called hyperparameter tuning, how to find a good hyperparameter for what you need. And there's a whole bunch of stories around that. In the end, that's you'll get in a full machine learning course. But yeah, this is a hyperparameter. Okay, so you say a priori, you know how many clusters you want, but of course there's ways to kind of choose. You know, too many you do overfitting, too less you don't capture the data, and that's really a big story in machine learning. So great question. Okay, clear about supervised, unsupervised? Yeah. So we'll see that. So sometimes you do this, and each cluster in the example we'll see, each cluster will have the kind of the centroid of the cluster, and you'll see what it represents. So indeed, in this application that I spoke about, where you take your customer data, right, and you've got like 3,000 customers, but then you want to give the marketing team, here are 7 personas of customer. A persona in the world of business and all that, yada, yada, is kind of, you know, a category of a person, you know, they have this and that and that and that, and they can then tailor the ad campaign to that persona. So that would be, say, the center of the cluster. Okay, very loosely. Of course, you run into a whole bunch of trouble when your data is not numeric. So I represent this as a matrix, and we love matrices. Everything kind of works as a table, as a matrix. But what if your data is not numeric? For example, you've all used ChatGPT or its friends, okay? The data is not numeric, it's textual, right? So there are many stories about how to convert that textual data to numeric. In a nutshell, for example, in the world of natural language processing, what you do is you do word to vec or some variant of that. So every word is mapped into a vector in R700, something of that order. Okay, so you got different vectors or different words, and you do that in a way such that say, for example, the word queen is next to the word king in that space, whereas the word automobile is far from it. Okay, and that also kind of helps the algorithms. It's a very loose field, machine learning. The beauty is that with just a bit of mathematical education and programming, that now you guys have both, you can enter it and you don't have to get a full formal education to then do something with it, both in industry and outside of industry. Okay, so ML data sets. Now, often, okay, if I now go and I work for Department of Agricultural Fisheries in Queensland and I do something very specific with, say, wheat, they're going to give me their wheat data set that I actually do this with some friends in a form. Okay, they're going to give me the wheat data set and it's going to be very specific to that domain. Okay, it's going to be a proprietary data set. Now, in machine learning, that's also true in the sense that if you work for Tesla and you're one of their 500 or 5,000, I'm not sure how many machine learning engineers they have, okay, then, and you look at their recorded video data, that's also a proprietary data set. But the good news about machine learning is that there are a whole bunch of open data sets as well. And these open data sets are not just useful for what we're doing now, which is education, okay? It's also useful for starting to train models. For example, the most famous data set is called the ImageNet data set. So the ImageNet data set has, I think, 15 million images, depends, some are labeled, some are not. There are kind of several subcategories, but a whole bunch of images. So often computer vision machine learning algorithms are trained on that open data set. And then you can fine tune to the data set for your specific application. So anyway, that's machine learning data sets. And the very basic data set that we'll speak about is MNIST, and that's used in almost any machine learning research paper, certainly up to 3, 4, 5 years ago. But machine learning is starting to move away from this. Still, for educational purposes, it's useful. So let's actually just do this. Let's hope it works. So I'll just create a new. So first of all, the package ML datasets is just a Julia package that exposes popular available machine learning datasets. There's some warning here about deprecation, but let's not worry about that. So that's a package ML datasets. And what we're doing here is actually asking it, give us MNIST, okay, and get the train data of MNIST. All right, and I'll speak about in a second about what train data is. And then let's do look at train images. So the train images is going to be big, of course. So train images is a tensor. It's a 28 by 28 by 60,000 tensor. Okay, what's a tensor? A tensor is just a matrix. Okay, not in the physicist sense, but a tensor is just a matrix with one more dimension. Okay, so you've got 28 by 28 and 60,000. Of course, it could have been that the interface for Julia would have been to give it as an array of matrices, okay, or something else. But it just gave it as one multi-dimensional array. So an array float 64.3, that's this tensor. So if we take, for example, the first one, well, I can't do that. I need to do a colon first. So here we've got our 28 by 28 matrix, right? So I took the first slice, the first image from this, all right? Okay, now what's the story about train and test? Well, the typical paradigm that you have in the world of machine learning, the simple one, a simple paradigm to look at is going back to this image here. all this data that we got here from the world is a training data, okay? But then after we train the algorithm, we want to test how it works. So, well, we can just go to the world and take one more piece of data. But often we would ahead of time do that, for example, 10,000 times. So we'd have 10,000 testing data. So people call this phase production. It's also test time, okay? Now, of course, there's a problem here. Today, we're soon going to train MNIST, but we're not the first and not the last in the world to have done this. Many people have trained MNIST and have used this test data that I'm going to get in a second. So MNIST has 60,000 training images and 10,000 testing images, okay? So it's no longer really an unseen test. It's already been used a whole lot. Okay, so just so you know, there's another paradigm which is separating the train into validate, and then you have train, validate, test. But again, that's in a full machine learning course. So what you would do is you'd optimize hyperparameters in the on the validation data, and only in the end you would touch the test data. Because if you touch it too much, you're cheating. Okay, I hope that's kind of clear. All right, so we did this, and let's also get the test data exactly just as we said. So here's the test data. Okay, so you see there are 10,000 test images. And of course, stop me at any time. So the size of the test images is 28 by 28 tests. And let's also just get this length. I think we might need this. No, just want to do this so it also runs. So n train and n test. Okay, we've assigned to each of these variables how many training. What's the size of our training set? What's the size of our test set? So let's just do some plotting. 2 years ago, this would have taken a minute or two. This is Julia 1.9. I think this should take about 10 seconds for Julia to precompile plots here. I'm not sure. So what we're doing here is we're just plotting the first 12 digits. So let's just see how we're doing that. And when you do this project, well, when you do machine learning in general, okay, the concepts you're going to understand pretty quickly because you're all smart. And then you got to go into the details, and often what you do in details is indexing, and do you get it right or not right, and the types of things, etc. So let's understand this just a bit. So first of all, we're using plots, and we're using measures. That's just a package that allows us to put spacing between the plots. I don't think that's important. And LaTeX strings, I don't think we're using that either. So that would have worked without LaTeX strings. So there is an array of train labels. Let's actually look at the array train labels. Okay. So the array of train labels has 60,000 labels. And guess what? The labels are the digits 0, 1, 2, up to 9, right? So each label matches the image, right? So this is the first 12 labels are 5, 0, 4, 1, etc. So we're just taking the first 12. And now let's plot each train data. So this is a kth train data. And when I say plot, the type of plotting we're doing here is a heat map. And for this, with the plots package, you also need to take the transpose of it and do y flip it equals true to see it correctly. That's not so important, but just to see it correctly. And you're creating 12 of these. So that's your 5, your 0, your 4, your 1, your 9, your 2, etc. Yeah.
So the train like the actual
Right. That's your wise, 100%. Yeah, and that's thanks for asking. That's good. So just to connect this to what we have here. So what we've plotted here are the first 12 rows of this thing. Now you say, hey, how's it a row? Well, let's just do a row. So if you take train data, this is your first training data, and let's just vectorize this. Okay, here it's a row. Okay. That didn't work well. Why not? Interesting. Train data. What did I do wrong? Oh, sorry. Train data one. Sorry. Train data. Okay. Train data. This is just a Julia postfix operator, right? So train data is not one. Train data has two things. It's a tuple where you have your features and your labels and your targets, okay? So if we take train data one, what we need to do is train data one, that's this thing, that's a 60,000 tensor of images. And if we take the first one, the first image, it's this. And if we stick it in a vec function, so vec function takes a matrix and vectorizes it. Don't ask me now if it's column-wise or row-wise, but it creates a vector from matrix. Okay. And here you go. So that's your 784-dimensional vector. And this guy sits in the first slice here, the first row here. Okay. All right. And yeah, when somebody created MNIST, so last year I worked in this, so I was, now I'm at 50%, I'm working more in statistics with Julia in pharmacology. That's in my non-UQ job. Last year I was on long service leave, and then I started getting working in industry a bit more. So I worked for a company that does fire detection with hilltop cameras in California mostly. So you got hilltop cameras, these cameras spin, every 3 minutes they take snapshots, they see fire from far away, they say, is it cloud or is it smoke? Or basically is smoke or not, and they say where. Okay, that's kind of the idea. So machine learning at scale in a sense, not too complicated, but really complicated. There are many things in industry, as you probably got from the other speakers, are not too complicated, but actually very complicated because there's just to make it work. So why am I telling you this? Oh, yeah, so we had to get annotators to look at images and say, put around the smoke of the fire, you don't see the actual fire, you see the smoke, say this is smoke, and you have to create software for this, right? So a lot of the work of machine learning, of creating the data set, is somebody looked at these 60,000 images. I mean, this is something that you can knock out in 2 nights with a lot of Red Bulls, right? You look at 60,000 images and you just say, what is the image? Okay? So that somebody annotated this. Most machine learning data sets that on tasks that try to mimic human level performance have been annotated. Okay, not all, because when ChatGPT, for example, is trained, it's not annotated. It's not that Wikipedia was fed into ChatGPT and then somebody put on the side what it means, but rather what they did is they did missing words, and ChatGPT learned how to fill in the missing words. So that's kind of the that was unsupervised learning, by the way. Okay, so there's no annotations. But yeah, some poor person annotated these 60,000 images. Okay, yeah.
This is
28 by 28.
That's the features of each pixel.
Each pixel is a feature. Yeah. Yeah, and if you have color, then the tensor would not be 28 by 28 by 60,000. It would be 3 by 28 by 28 by 60,000. And if you use, and the 2 most common machine learning packages for deep learning are, by the way, and they're not in Julia, PyTorch and TensorFlow. Some of you would have heard these words. So in one of them, the order of where you put the 3 is different than the other, etc. Okay, but you would have had another layer because each image is 3-dimensional. But still, you treat each image as a vector. Okay, let's move on. So we've done that. We've seen the data a bit. Now let's see the data in a slightly different way. And what I'm doing now is not something you do with really big data sets that are not toy data sets like the MNIST data set. So what I'm doing now is I'm really just I'm vectorizing each of the images, okay? And then I'm doing VCAT, which is kind of vertical concatenation. I put one after the other after another. I'm really putting the big data matrix exactly like it is. I just want you to see the big data matrix, and Julia's kind of fighting here, etc. But we'll see it in a second. So this is going to be a 60,000 by 784 matrix. So again, just moving to this. This is going to be, we're now going to see this thing. Okay, let's see it. Well, while it's waiting here, let's just see it here. So here's what it's going to look like. So why is this pattern? So again, each row is 784 dimensional, okay? And the number of rows is 60,000, right? 6 times 10 to the 4. So what's this pattern that you're seeing? Why are we seeing it? Why are we seeing this pattern? So look at the images and just think a second. Yeah.
replace why this would be.
Exactly. Yeah, perfect. So, but the thing that happens is the nature of the images. These have been pre-processed. And by the way, when people create data sets, a lot of work goes into pre-processing, right? So these are not digits like you'd have them in your pattern recognition system that Queensland Police finds on your license plate, right? This is kind of, these have been process centered, et cetera. And because they're centered, you've got a lot of darkness here and a lot of darkness here. So a lot of zeros there and a lot of zeros there. And then that's what you're seeing is row by row by row by row, right? You have 28 rows. Okay, that's all. Not much to it. But the point is, this is kind of your whole data matrix. When you do machine learning at scale, you don't have the luxury of putting your whole data matrix in one plot typically. I mean, it's just too many features, too many data points, etc. Okay, so and here is if you sort it. Let's run this. Why not? But let's just look at it as it runs. So what we're doing now is we're sorting by the sort perm. So the function sort perm takes an array and then returns you the permutation that if you would reorder by the permutation, you get a sorted array. Okay, so what you have here are the first ones. These are the digits 0, and these are the digits 1, and these are the digits 2, and these are the digits 3, and digits 4, etc. Okay, you've got 60,000 divided by 10. This is a balanced data set. Balance means that 60,000 divided by 10 gives you, which is 6,000, is roughly, this is approximately balanced. Okay, it's the number of images of each digit. Okay, there's a whole, again, when you do machine learning later on, there's a whole bunch of discussion on unbalanced data sets. Okay, and that's kind of important too, because for example, when you look at, say, cancer patients, right? You take 100 people, luckily, most of the 100 people, if you do an MRI or something like that, do not have cancer, right? And say only 1% has cancer. So that's a very unbalanced data set. Of course, you can create a machine learning algorithm that looks at the person and just says, hey, they're healthy, okay? And you'll have 99% accuracy. But that data set is unbalanced, so you need to take care. Okay, so we won't speak about dealing with unbalanced data. That's a whole issue. So my whole point about just showing this plot here is just so you see that even at this scale, when you look at the data, there are kind of different patterns that emerge, right? You see the digits look differently, okay? And we would like, obviously, the computer to be able to differentiate between digits, and let's go towards that. How are we doing for time? 5:38? I think we're okay. All right. Oh, I guess before we do that, let's get a taste of unsupervised learning. All right, so that was just to feel the data. It'll probably be after the break, we're going to run linear regression on this, which is a supervised learning algorithm. I mean, you know linear regression, but we'll do it at scale here. And we'll see how we can classify if a digit is 0, 1, 2, 3, 4, up to 9. Okay, but let's now that we understand this data, let's go to unsupervised learning, to this world. Okay, to the world where we're going to look at a clustering algorithm and a data reduction algorithm. So let's actually start with the data reduction algorithm. Okay, so what we're doing here is, and of course this can be a huge lecture on its own or multiple lectures, etc. The idea of data reduction is to take this 784 dimensional vector, okay, which represents an image, and to project it onto a lower dimension. As I'm speaking, let me actually run this code. Okay. Let me run this code here. Okay. And here we're going to use a package. This comes from a package called multivariate stats, multivariate statistics, and we're going to use the fit method on a PCA object. PCA means principal component analysis. And what we're going to do is we're going to ask Julia, well, from this data, where in this case, we're going to give the data, it's not going to be X, it's going to be X transposed, because PCA doesn't like to have observations and features. It likes to have features and observations, okay? But that's just a matter of convention. So we're going to give it X transpose. And we're going to we're going to do a fit of PCA. Then we're going to get the projection matrix of PCA. And what this is going to give us is a matrix M, and that matrix should be 2 by 784. And then you come with your odd digit to the matrix, and you put that 784 thing on the matrix, and you only get 2 coordinates. So we reduce 784 coordinates to 2. Now, why do such a thing? All right. So let's see if this ran just to see it here. Yeah, why not? Let's see it here. So I'll look a bit, we'll look at the output a bit, and then we'll just analyze the code just a bit more. So what I'm doing here is, even though when I ran this PCA, I did unsupervised learning. I did not care if its label has digits 0 or 1 or 2 or 3 or 4 or 5 up to 9. When I ran afterwards, when I'm plotting it, I'm only going to take the data points that have, for example, digit 0 and digit 1. So let's just focus on this. Ignore the fact that we have 10 labels. Assume it was just binary classification between images of 0 and 1. Okay, and we ran it through PCA. The nice thing about two coordinates is what fits on the screen, right? A simple, stupid two-dimensional or three-dimensional, if you'd like, beings can see this, all right? And we can see that, for example, this point here, this one here, okay, that is one image. Of course, all of the data of the image, most of it is gone. But still, that image, if we'd like to describe it in the language of this transformation, of this linear transformation from 784 dimensions to 2 dimensions, it has principal component 1 being this, and principal component 2 being like -3 here, okay? Those principal components on their own don't mean anything. But when we look in them in total, well, I see something quite nice here. I see that all of the digits that were originally, and principal components didn't know if it's digit 0 or digit 1. I see that all of the digits that were digits 0 were placed in this cloud. And all of the digits that were digits 1 were placed in this cloud. Okay. So in this case, for example, say I now want to do something else with this. I want to do classification. Well, I can, for example, just stick a line between the two and say, if it's on this side of the line, a line is a hyperplane in more mathematical terms. If it's on this side of the line, it's a digit 0. If this side of the line, digit 1. Okay, that's one thing you might do with PCA. But there are many other uses. So first of all, and you can also just treat it as a visualization tool. Again, the value of the principal component itself doesn't mean much, but the relative value means a whole lot. Okay. Another thing you might do is actually when you want to cluster images. So we haven't seen clustering yet, but we will soon. So when you want to cluster images and they're very heterogeneous, it's actually hard to cluster on the original space. So you do a reduction to principal component space. Okay. And then you can kind of, everything that was a bottle will look close to a bottle, and everything that was a phone will look close to a phone. Right. So here, for example, should we have run a clustering algorithm, then zeros and ones are quite well separated. Okay. Of course, 0 and 1 is a success story here, but if you go, for example, the digits 2 and 3, at least when we do PCA to 2 principal components, we cannot separate well between 2 and 3. All right. And there are generalizations of PCA. There's nonlinear PCA, so this whole data reduction thing. Now, I'm not going to go into the mathematical details of PCA. Okay. A great course to do is anybody doing this now? Fred's course, the math, the numerical linear algebra and optimization. Recommended if you want to, if you like this type of stuff and you want to add stuff to your tool set this semester, next year, numerical linear algebra and optimization. So you'll do a whole bunch of SVD, singular value decompositions, things like that. That I know that Paul Bellet spoke to you about it even weeks ago, right? He showed you his picture with SVD, etc. But you'll understand the mathematics of PCA. Yeah.
We don't necessarily know like how they relate to the original feature.
No.
It's just part of the magic.
That's part of the magic, right? But also, if I'm this baby on the island and there's an image of a bottle, right? And then you give me a bitmap of images and you say, pixel, 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 I also don't know, right? So the PC1, PC2 is a different representation of that, but we've of course lost. Now we don't have to do PCA. The way I did it here was max out dimension equal 2. If I would have done PCA with max out dimension equal 3 or 4 or 5, it wouldn't have been as plottable. Well, with 3 you can sort of plot it, but after that we're kind of in trouble. But of course you might get more separation. Okay, and actually, if you get to this task, which is perhaps a slightly harder task of, we're now in your project, part 2, the machine learning part, and you go to option 2A, is like a difficult menu. That's like what I feel today when I go to order. It used to be that you speak to the waiter, and now you got to use a phone, all this stuff. So you guys the same, make all kinds of options. So say you ordered option 2A and you go to task 2.4, then what we're asking you here is to take MNIST, to do PCA, okay? For 2, you already have the code. We're giving you the code, okay? So, you know, you need to do smart mixing and matching of the code, okay, that we're giving you, okay? But do it also for 5, for 10, for 20, and for 50, and then carry out classification on that. You still haven't seen classification, all right? But that means that what we're doing here is like an intermediate step, okay? Any questions about this code? I mean, there's a whole lot here, but basically it's mostly code that's here to kind of, after we did PCA and we got the matrix, let's actually look at the matrix M, the projection matrix. So you see this matrix, oh, okay, I said it's 2 by 784. We apply an image to M transposed, okay? So M transposed is what converts from 784 dimensions to 2 dimensions. Okay, so this is like, these are like the principal components. And there's of course more to say about PCA, but we won't do that now. Can I move on to next one? We'll take a break in a minute. We'll just do clustering. So the other bit of unsupervised learning I want us to enjoy. So here there's again, we're using a package. We're not doing it manually. By the way, if you go to my Statistics with Julia book, then there's code that we do it manually, PCA and clustering. These are not complex algorithms, okay? So PCA, basically, you need to compute the eigenvalues of a matrix, okay? So, and I mean, computing eigenvalues is a complex algorithm, right? But we're using the package for that, okay? So numerically computing eigenvalues. And clustering, what's happening here? So we're using the clustering package, okay? And we're saying, please do run a clustering algorithm on the data. Now, again, the clustering package likes to have the data X transposed. So not 60,000 by 784, but 784 by 60,000. And the name of the clustering algorithm is called K-means. Has anybody heard of K-means before? Okay, Matthew, others? Oh, sorry. Oh, that's just the interface. So it's kind of, you know, some like oranges, some like apples. So some people in the world like to have the observations and the features, and some like the features and the observations. I mean, that's just how they've decided. And when you go and use in scikit-learn in Python, this is all done in scikit-learn in Python. Scikit-learn is a very popular package in Python that gives you all of this, right? You need to see, hey, do they want it like this or like that, etc. So, or in any other setting. So K-means, the algorithm K-means, K here is actually the hyperparameter that you asked about before. K is how many, let's go back to this. It took my colleagues and I about 3 hours of meeting to discuss this figure, not to draw it. So, so please, I want to use it a lot. So this is in the other book, which I recommend you, and that's the Mathematical Engineering of Deep Learning. So what I'm saying here, you can also go to, if you go to Deep Learning Math, then chapter 2 and chapter 3 really, you don't need to read them for the project, but if you go to chapter 2 and chapter 3, then that's the content, well, the content that we're using is a subset of that as well. But that doesn't have code, this book, that just has principles, okay? So here, K, well, if you're going to cluster digits, what's a good K? 10. I mean, so here you have a priori information. These are not customers of some company that you don't know and the company doesn't know. So we're going to do 10 clusters. So we're going to run a K-means algorithm. And what that algorithm is going to do is it's going to give us this thing called a cluster result. So let's look at it, cluster result. So, you know, it's returning, first of all, let's see what it is. It's a K-means result, okay? That's a type of this struct. And let's just print it. Okay, well, that's not very informative, but let's do field names of this. So let's see what's the fields of cluster result. So these are the field names. So what we get there is one important field is the centers. So the clustering algorithms gives us 10 different centers, so 10 different 784 dimensional vectors that are considered to be the center of the cluster. So again, images live in this complicated space, 784 dimensional space. There's some point there that it has decided is a center of a cluster. And it also tells you, well, each image, which cluster is it in? So it tells you how to exactly do this sorting for clustering. So if we plot these centers, okay, so we're now going to plot these centers. So this is just plotting the 10 centers. These are 10 images that don't really exist, okay? Each one is actually with k-means. K-means is a simple algorithm. It's a Euclidean algorithm. So this thing, which I think most of us would agree is a 1, I mean, maybe somebody will get mad and say it's a 7, but no, I think it's a 1, all right? So this 1 sits in the center of other images, not necessarily 6,000, right? There are 6,000 roughly ones, but you know, it might have pulled others because it's not perfect, okay? And that's just a Euclidean mean of the coordinates. So you can sum up all the vectors and divide by the number of vectors there, okay? So the Euclidean mean you do is just a mean on each coordinate, okay? Right? So, I mean, what's the Euclidean mean roughly of San Francisco? Think the Earth is flat for a second. I mean, maybe you do, so don't think. Maybe just the Earth is flat. Okay. So San Francisco, I don't want to offend anybody. San Francisco and Brisbane and Auckland in New Zealand. San Francisco, Brisbane, Auckland, New Zealand. Euclidean mean. Maybe it's a bit hard, but maybe something like Fiji. Okay, Fiji. All right. So it's just the center. So this one here is just this is your centroid or your center. Of course, we didn't get all digits represented. Two things that look like 9 are appearing, all right? But the clustering algorithm discovered that for us, right? So if we take now hieroglyphics or language we've never seen, all right? And you stick it in, well, you might see representatives there, okay? But of course, it also clustered the data. So that's clustering for us. Yeah.
Yeah, I have no idea.
No, it didn't. And so we'll go to the break, but I'll just put this up. So if you go to chapter 2 of deep learning math, so chapter 2, of course, there are many books, but you know, like any academic, I like my books because I try to do it in the best way possible, right? But there are much better books by much smarter people, but this one tries to give one perspective, all right? So here, if you go to the section that actually, I'm just going to pull up an image. So this is chapter 2, which is machine learning. This is a deep learning book. We haven't spoken about the deep learning at all. And there's a section called The Taste of Unsupervised Learning. And the first thing we do is we just describe in a page and a half how clustering works. And here is basically how it works. And I'll just use this image very quickly and explain, all right? And then we'll take the break, all right? So I'll just describe how k-means clustering works. So in this example, we're not clustering images that are 784 dimensional. We're only clustering points that are 2-dimensional. In our case, you might have thought that we would have done PCA when we're clustering based on the principal components, okay? But it couldn't be just that we're clustering people based on height and weight, for example, or something like that, all right? So, and again, there was a hyperparameter, like was asked. The hyperparameter is 3 in this case. So the way k-means clustering works is, first of all, you just initialize randomly 3 centers, like the circle, the triangle, and the green plus, all right? Now, how do you do randomly? Well, one way is just to choose 3 random data points, okay? A different way is to look at the dimensions and to choose something uniformly in the middle. And then, so that's the first step. Then what you do is you run over all the points and you see all the ones that are closest to the circle, you say that they are part of the circle cluster. All the ones that are closest to the plus, you say they're in the plus cluster, and similarly for the third cluster. So you've already got some clustering. Once you've done this, then what you can do is you can, again, go back to mean computation. So it goes from here to this, okay? What do you do now? So now that we, for momentarily, assume that these guys are a cluster, let's now compute the Euclidean mean of this cluster. So this big triangle is going to move just a bit to be the Euclidean mean of these clusters. So we shifted it just a bit. It's not really visual, but well, you see that this guy moved, okay, to here. So each one is now at the center of its cluster. Well, you guessed it. Next step, what do? we again see now who are the closest to it. And then we get to the next step, and either if there are no shifts, or we just decide to stop, or shifts are less than number of changes less than epsilon, etc., we say these are the clustering. Now, actually solving this, if you would formulate it mathematically, if you'd say there's some objective that you're trying to minimize, the objective could be find the centers and find the subsets, is actually an NP-complete problem. NP-complete means it's not computationally tractable, really. Clustering is a heuristic. It was invented. It's not hard, right? It was invented in the 60s, and it's very, this algorithm k-means is very simple. So machine learning algorithms can sometimes be simple. This is one of them. Okay, that's clustering. All right, any more before break? Okay, let's take a break. 5:56. Let's start at 6:05. Okay. Home, is there anybody at home? Oh, we got people at home. I hope you can hear, because I asked it first if you can hear at home, but there was nobody at home. There was one person. Yes, you can hear. Thank you. Yeah. answers to these two questions. Well, comment on the two questions. Hi, Tom. I hope you can hear. Okay, sorry. So, any questions beyond so far? Okay, just there was a question about the stopping criteria. Yeah, so the basic stopping criteria here is natural. This is a type of algorithm that really tells you that it's stopped, because if now you have nowhere to go, that means that, you know, there's, when we were here, we were in this step, it's not visible in the image, but there was, for example, a red triangle that was actually closer to the black circle center, right? Or something like that. So it shifted. But here we have kind of nowhere to go. Okay, so that is a stopping criteria. Other machine learning algorithms, we'll see that, hopefully we get to it today. We need to, okay? So other stop, not the end of the world if we don't, we have tomorrow as well, but other stopping criteria are that the steps have diminished and they're less than epsilon. Okay, for example, you can look at the difference, look at the circle, this, you see, there was a huge step in the centroids between this first row, that's the first iteration, and the second iteration, right? I mean, at least it's very clear with the black circle, okay? With the big black circle with the centroid. But between here and here, there was only a small jump. So say that this had a lot of data and also a lot of coordinates. This is just in 2 dimensions, right? The clustering we just ran was on 784 dimensions, right? So we can't visualize it, okay? So, and we can probably interrogate the algorithm and see how many steps it did. But one way is just to say, well, if the centroids just didn't move too much, so you often, then that's another, if you could say, a hyperparameter or an algorithm setting, so a stopping criteria. More questions, thoughts? Okay, so that was our adventure in unsupervised learning, but we'll go to supervised learning. Okay, so our goal now is going to be to take the digits, the images of the digits, and create a classifier that will tell us what the digit is. Okay, and we'll do that. We'll do that from first principles. The common way that you would do it today is using something called a neural network. Okay, and specifically since it's images, you'll probably use something called a convolutional neural network. We'll just use a neural network that has an identity activation function and only has one layer. So that's linear regression. Linear regression is a basic case, or least squares linear regression is a basic case of neural networks. Neural networks add more layers and there's more stories there. And that's deep learning is a study of, or the application of neural networks. So is deep learning machine learning? Well, you could say that deep learning is one set of tools within the world of machine learning. But today people just use the things kind of interchangeably because for the past 15 years, deep learning took over. It's just become so good. Okay, that's, and basically you are going to do some basic deep learning, but at the moment it's kind of degenerate. So here's the strategy. There's a whole bunch of text here. You can study it later. I'll just say roughly what we're doing. So we're doing this linear model here. Okay. So what do we have? So this superscript I, that's the ith observation. We have 60,000 of those. Okay. And let me make this a bit bigger here. And for the ith observation, we're going to also create a label, which is the ith label. Now, when you saw the labels before, if I go here and I go to like here, let's do again train labels. Let me just take the first 20 of them, okay? So here are the first 20 train labels. These are the first 20 train labels. Oh, what I would like to do now is I would just like to do, and this is multi-class because you're 10 possible labels. I'm going to just do a binary, so 2-class, a binary classification for, say, if something is a digit 8 or not 8. So what I'm going to do is I'm going to do the training labels and I'll do like, does it equal 8? Okay. So most of the digits are not 8, and these 20, only this one was 8. All right. And I can do that. All right. And just to make things a bit simpler, so I'm also going to do, let's just do 2 times this thing minus 1. And that's just one way of transforming. That's not working because I need a dot minus, because Julia doesn't do minus for vector and scalar. Okay, so you see, I've got all negatives, all are negative examples, all are not 8, but only this one is an 8. Okay, so momentarily, I'm going to say I'm not going to deal with multi-class classification. I'm just going to do single class. Is something a digit 8 or not? Okay, and that's going to be part of our strategy for this specific classification example that you'll see, for this supervised learning example that you'll see. All right, so and we're going to do this not just for the digit 8, we're going to do it also for the digit 5, and we're going to do it for each of the 10 possible digits. And of course, for the digit 5, you see, this is the digit 5. This first one is the digit 5, and then we have a digit 5 down here, down the road. Okay, etc. So this is a data transformation I will do. So this y here is exactly this. That's explained in the text. This y is either a positive 1 or a negative 1. Basically, what I want to do, this is your simple, well, it's not simple. Simple linear regression is if it's just beta 0 and beta 1. Hold on one second. This is your multilinear regression. This just says this yi, let's hope that is some parameter beta 0 plus some parameter beta 1 times this thing. And let me explain what this thing is. This here, the x sub j, is the first pixel, And we have 784 pixels. And then when j equals 2, it's the second pixel. When j equals 3, the third pixel. We go like this on all 784 pixels. So how many parameters do we have here? How many parameters? 785, right? There's one parameter for each pixel. Okay, it's beta j, and one parameter, which is the intercept. Okay, which you sometimes in the world of machine learning, the most overly used word in machine learning is bias. Okay, so you sometimes call it the bias. Okay, don't confuse this with what people call machine learning bias when machine learning kind of, decides that people from a certain gender do more than something, or from a certain race do more than something. So that's data bias, that's ethical bias. Okay, this is just a bias, the intercept, right? So 785 parameters. Did you have a question?
So this is only for 0. Like
this is only for binary classification.
Right. So if you want,
we'll get to multi-class. Okay, so machine learning, supervised learning algorithms for classification can be binary classification or multi-class classification. Okay, we're going to do binary classification and fuse those binary classifiers into multi-class classification. Okay, so say we did this on data to choose if something is a digit 5 or not a digit 5. Is it a digit 5, not a digit 5? All right, so we had this equation for 60 I ran from 1 to 60,000. We had 60,000 of these. All right, and we're going to do least squares. Okay, sorry, the least squares, linear regression. That's what we're going to do. And we're going to find the best beta 0, beta 1 up to beta 785. We're going to find the best 785 parameters that fit this yi, either +1 or -1. How would you convert this to a classifier? So now I take an image from the world. I take some image X. You ask your friend to draw an image, and they draw you an image. That's this X tilde. Right? So 784 dimensions a pixel. They drew an image and you vectorized it, okay? And you stick it in your model. You stick it, we're gonna know what these betas are, and you're gonna get some predictor. How will you say if it's a 5 or not a 5? What would be your decision rule? So, yeah.
maybe it's bigger than 0.
Yeah, exactly. And that's why it was nice to go for +1, -1. We could have left it as 0 and 1, but you'd see if it's positive, right? If this linear combination is positive, you're going to say, that's a positive example. If this linear combination is negative, that's a negative example. Okay, so you've created some threshold. All right, we could have done it with 0 and 1, but then the same. Okay, so this is it, except we need to find those betas. This is it as a mechanism of finding a classifier to know if something is 5 or not 5. Okay, it's not a classifier that you can use in the industry, because you'll see that when we combine this all, we're going to get about 86% accuracy. But still, 86 is much better than your kind of naive default accuracy. What would be your accuracy on MNIST if you had the arbitrary random classifier? What would be your accuracy? How much, Matthew? 50 is it's binary. Oh, you're right. For binary and for 10 digits, yeah, 50, 10%. Exactly. Yeah, but for binary 50, exactly. It's going to be 86% for the total, not for the binary. But yeah, okay. All right. So what we do now is we use good old linear algebra, good old statistics, if you want to call it, etc. And let's go through this quickly. And this is so when you go for the more complex models, for deep learning models, this actually doesn't work. But for the linear model, this works well. So what we're going to do is we will just call the prediction what I have here under the cursor. This is your predictor. This is a vector of 1 for the bias or the intercept, and the vector of the observation, and you do the inner product of that with beta. So this is your predicted observation, and this is your seen observation. And you take the L2 norm, you take the sum of squares loss. This is the sum of squared loss. So this is here what you call a loss function. And if you had a beta which you like, which you think does a good job, then that beta is going to minimize this thing. Because, for example, if it had a perfect prediction, what would be L of beta if it had a perfect prediction? 0, right? It's not going to be 0 really because things don't fit exactly on a line, but if you had a perfect prediction, it's going to be 0. Now, squared loss, we like also, Gauss liked it 220 years ago mathematically because you can also take derivatives and do things. When you go to other cases, you might want to take absolute value loss or other losses, and then things are not differentiable. You don't get this kind of nice closed form solution, which we'll use. But we could do that. And if you do this, then you can also take your data and take this matrix here, which is almost the matrix that we saw here. So it's almost this guy. It's almost this guy. This is like your data matrix, right? The 60,000 by 784. But let's just add, because we have a bias, let's just add a bias. And that's the column of 1, okay? So it's 60,000, N is 60,000, and 60,000 observations by 785, right? And that now allows us to do A times the matrix beta, and that gives us our prediction. So this is all your data is in this matrix. In the world of statistics, you call it the design matrix. Okay, in machine learning, I don't know if you really have a name for it actually. Okay, so the loss you could treat as this thing, which is this is a vector which is this thing I'm highlighting is a 60,000 long vector. Okay, subtract from it your actually observed vector. Take the L2 norm squared, okay? You could have think of subscript 2 here, but no need, okay? Which you can also write like this. Okay. Now, interestingly, or some of you might have seen this, but probably many have not, this loss, oh, and here's how you create the matrix A, okay? So here's programmatically, let's actually do this. Let's create the matrix A. Okay, so it has this ones, all right? So size of A is 60,000 by 785. Okay, so this loss, you can actually also compute the gradient of the loss. Now, with deep learning, with modern machine learning, and this linear regression is kind of the simplest special case, everybody wants to know gradients all the time. Because the way that you train more complex models, neural networks, which would be this plus some more complexities, okay, is by moving in the space of parameters. The space of parameters here is R785. You move in 785 dimensional space, moving in the space of parameters, trying to minimize the loss function. Now, in this special linear regression case, least squares case, we're actually going to use nice, good old linear algebra that has been known to humanity for 200 years and been really written nicely in the past 67 years, okay? And we're actually going to get we're not going to have to do gradient descent. But keep in mind that you can do it with gradient descent. Now, what is gradient descent? Gradient descent means that you live in this landscape that's, let me actually just open a figure. So we'll go here. So you'll go to chapter 4 here too. Or let's even go to chapter 2, Principles of Machine Learning again, and just open some figure. Okay. So here in this figure, okay. So Ignore for a second all the jaggedy lines, you know, the gray line and the red line and the blue line. Okay, just look at the contours. This is a contour plot. Okay, you know what a contour plot is? So we're plotting a function from R2 to R. We're plotting the loss function in this case. This is not the same case that we have there with 785 dimensional problem. This is only simple linear regression, a two-dimensional problem, beta 0 and beta 1. Okay, these ellipsoids are, so this function is a quadratic form in beta 0, beta 1, and it actually has this nice form, and this is a minimal point. Okay. Gradient descent says, and so, right, so think of a topographical map, etc., and that's what you're plotting. Okay, you could have done a kind of a 3D plot of this as well, or if you really want to get into it, you have a 3D printer and just plot, you know, sculpture the bloody thing. But let's just stay like this, all right? So gradient descent, you start at some arbitrary point, like this point, and what you do is you then look, where is a gradient? The gradient is a vector that points in the direction of steepest ascent. So you then go, oh, this is steepest. No, I don't want to go there. You turn 180 degrees to the other direction and you go there. Now, because we're in a computer, this is not some analog computer that works fluidly, okay? You have to take steps. So then you say, well, I'm not going to move epsilon, that's like a true epsilon. I'm going to move some little step. And you move in the direction of the gradient, okay? And you do this again and again and again. And all the time you can recompute your loss. So you don't see the whole thing. You just see, let's say you're just moving on this red line. You just see where you're moving, okay? By the way, if you do this here, you'd move like 3,109 times. If you take these very small steps, take steps that you don't see the whole thing, but every time you compute your loss and you see, hey, how am I getting? How am I doing? Then you got to this point and you say, hey, I moved, but actually, you know, because it's a local minimum. In this case, it's a global minimum. Okay, so you can't move anymore. So you're really not moving, or you're just moving kind of in place. Then you say, oh, I stop. Okay, that's how you stop gradient descent. Now, what I just explained is when your buddies, and that might be you very soon, train a deep learning model on a GPU, often a graphical processing unit, because you need a lot of compute for this. Okay, it might be on the cloud or it might be on your computer. Okay, what you're doing is gradient descent. Of course, not the simple one in 2 dimensions, but even now in the other notebook, we're going to see it in 785 dimensions. Okay, so you move in the direction of the gradient. Of course, there are more complex algorithms. There are second order methods. There's methods that look at the curvature, etc. But for complex deep neural networks, gradient descent or some variance of it, that's still the norm. That's still what's used. Okay. What this figure also goes to show you is that these steps, and let's actually look at an equation of gradient descent. Here it is. So here the parameters are called not beta, but rather theta. Okay. So and t are iterations of the gradient descent. And your loss function is called here c. So this is the gradient of the loss. Okay. The gradient descent algorithm is a simple equation which says the next iteration is going to be what you had before minus some small value, which you call the learning rate. It's going to be this thing that you multiply the gradient with, that's a scalar, times this vector that's called the gradient. Okay. When people compute things in deep learning frameworks, a lot of the computation, okay, if you've heard of those things, a lot of the computation is actually to compute this thing. So machine learning frameworks, PyTorch, TensorFlow, etc., they work with the back propagation algorithm to compute the gradient. So computation of the gradient is a thing of its own. However, in our little fun world of linear regression, there's actually an explicit expression for the gradient. So you can use some matrix calculus and see that the gradient is, so this is a vector, 2a transpose times a beta minus y. So it's a function of where you are in beta, and you actually have an explicit expression for the gradient. Okay, so if you were doing gradient descent to solve this problem, you could do that. However, since this is least squares, this is not a complex model where things are intractable and you need to really do gradient descent. We don't even do gradient descent here. I mean, you can, but we don't. We will use it for the next complex model just after. What you do is, well, how do you solve for a minimum? Equate the gradient to 0. 0 scalar or 0 vector? Vector, right? 0 scalar is like a syntax error, right? It's a vector, right? Okay, good. All right. So equate this to 0 and get this thing. All right. and use distributive law. Don't forget that matrix multiplication is not commutative, etc. Move this to the other side. And then what you get is this thing, and that's called the normal equations. Now, really, to show that something is a global minimum, well, to show that it's a local minimum even, you need also second order conditions. You need the Hessian matrix to be negative definite, okay? And positive definite. Minimum positive definite. Yeah, positive definite, okay? But we don't do this, all right? And keep in mind, this is just for a local minimum. But these types of problems are also convex, and hence the local minimum is also global minimum. Other more complex problems really used in deep learning frameworks have many local minima. But somehow with the magic of deep learning, it doesn't matter if you end up not in the best local minima. You're kind of in one local minima and it's good enough. Okay, so it's a very dirty science. So when you get this thing, you can actually now multiply this thing by the inverse of A transposed A. Now, A transposed A, it's called the Gram matrix. And if A does not have linearly dependent columns, then this matrix is actually non-singular. This is a square matrix. And this whole inverse is called this. These details are not so important. I'll just so you know that there's math there, and you can fill them in if needed. This thing is called the pseudo-inverse. Okay, it's denoted A dagger, the Moore-Penrose pseudo-inverse. Right. So the point is that to minimize least squares, to find beta, I mean, math is also just about finding nice structure, but then we can move it into the Julia language in a second. So to minimize beta, you can do the pseudo inverse times y, and you get the, well, to minimize the loss, sorry, to find the beta that minimizes the loss. Okay, you can do this. All right. And let's run this code. So we're actually, I gave you this whole story about gradient descent, but we're actually not using gradient descent here. We're actually just using a numerical linear algebra routine, pinv. Okay, so if I do pinv of A, so again, A is this matrix, the 60,000 by 785 matrix. I can use a function that comes from the linear algebra package. It's called pinv, pseudo inverse of A. And it gives me a matrix that's going to be 785 by 60,000. So what this matrix does is if I then multiply this, if I then do this and multiply it by the y, okay, so we'll see the y in a second, right? So, I guess I'm not doing it in one go. So let's do it manual. Let's do it ourselves here. So I'm going to get my y. Hold on. This is, for example, I'll just copy this. And let's call y this momentarily. But not the 20, let's go big. 60,000, okay? We've got y, 60,000 ones, negative ones, about 1 in 10 is a positive one, right? Because it's a balanced data set. So if I do pinv A times y, it computed the pseudo inverse, and it's going to give me now the beta. So these 785 things, and let's actually also plot this guy, just so we see something. Okay. So these 785 values are the beta coefficients per pixel. Okay. So we've got 785 values. Okay. And most pixels are close to 0, but some pixels beta is very positive and very negative. All right. And basically, if I take this beta here, so let's call this, this is very dirty what I'm doing, okay? But let's call this beta 5. But let's be a bit less dirty. Let's do beta 5 like this, because we like style. Okay, so let's do beta 5, and that's pinv A times y. Okay. Where's my model? Is it pinv A? Is it y? Is it beta 5? What's my model? What's my model parameters? Beta 5. My model is the algorithm that takes your data, some new image that has never been seen, okay, and multiplies it by beta 5, okay? And then what does the model do? The model then sees if beta, if that thing is positive, it's going to say it's a digit 5. If it's negative, it's a digit 0. Okay, that's all. That's the thing. Now, what I did here with the pseudo inverse, etc., is because we're in the School of Math and Physics and we like math, you know, you can do it with pseudo inverse. No, you can actually do it for small problems. But in real machine learning, you're not going to do a pseudo inverse, because a pseudo inverse, it actually computed this thing. It did it in a smarter way. It used singular value decomposition algorithms or QR factorization. It did all kinds of linear algebra bells and whistles, okay? But you're not actually going to do this. You're going to do gradient descent. But now we're seeing it using kind of the linear algebra way, and I like the fact, and maybe you do too, that we can actually do it for MNIST. So let's now just repeat this thing in a slightly more orderly way. So I'll say what I'm doing here. So this bit of code, first of all, it uses the Flux package. Now, Flux is one of Julia's deep learning framework packages. One of Julia's deep learning framework packages, like a parallel of PyTorch and Python or TensorFlow, which is available in multiple languages. All right. So that's what Flux is. We are just going to use one function from Flux at the moment, which is called one hot batch. One hot batch is just a function that takes, if you do, if we do this a second, so let's do it down here. One hot batch, and let's take, say, 7. It's just a function that kind of makes you puts things 0 or 1 for the digit 7. So we don't even need to use that function so much. This small little function just takes an x and says if it's true, then take a +1. If it's otherwise do a -1. So that's not so important. And why these are y dat k. So if you do y dat of k, now if I do y dat of say 7, I'm going to get, again, we already did this manually, right? These all are not 7. Okay, let's do y dat of something else. So you can do y dat up to 0 to 9, but y dat of 3 is, you see, this example is a 3 and this example is a 3. So not so important. We already did most of the work. What we're doing here is we're now computing 10 betas together. Because we don't have one model. We said we're going to break up the problem to 10 binary classification problems. We have a binary classification problem to see if something is a 0 or not a 0. To see if something is a 1 or not a 1. If it's a 2, not a 2, up to a 9, not a 9. For each one of them, we're going to take the pseudo inverse, that's a dagger, times this data. And that's going to give us our list of 10 betas. Okay, so now we have here a 10 element vector where each element is 785 dimensional, is this thing. Okay, so by the way, it's kind of just a nice feature that we only had to compute the pseudo inverse once. By the way, it doesn't matter much, but just so you see it. Okay, so with that at hand, now let's actually use this thing to create a linear classify. So let's understand this function linear classify. Okay. So what does it do? It takes, first of all, we have the argmax function. The argmax is just, if you just do argmax of -3, 4, 8, -2, okay, it's going to give you the index that is the maximal index. All right, that's what argmax is. I mean, not a complicated function, just a Julia function. What we're going to do classification is, since we have here, we have 10 here. Let's go back to this ugly plot. Sorry. Oh, I see. One sec. We have 10 betas like this. Each one like this. Ignore the label y1. Each one is like a beta, right? There's a beta for the digit 0, beta for the digit 1, a beta for the digit 2, after a beta for the digit 3. We'll take our unseen image, 784. We'll push it through beta. Well, not it and the 1. 1 is for the bias. So 785. We'll push it through the beta. We'll get a predictor. What is it? What would be, and so we'll do this for 10 of these. So you've got 10 different betas like this, and now you've got like 10 different, let's call these things, and that's what they're called, 10 different logits, 10 different scores. So I did it for each of my 10 betas. Say I got -7, 5.3, 8.9, 2.3, 17.4, 21.8, -13, right? I'm giving you values of that image times beta. Which one would you choose as what's the correct digit? The maximal one, right? That approach is called one versus rest multi-class classification. Okay, so it's you take a binary classifier. For each one, you got like the score. And each time you just checked what is it, and you chose one with a maximal score. All right. It's a heuristic. Machine learning is one big heuristic. Okay, but it's worth a lot of money these days. These heuristics. Okay, not this. This is no, but the newer stuff. Okay, so if you do that, and that's pretty much what the function does. So what we've highlighted here is you've taken the image. This is really your classifier. You're vectorizing a square image. Okay, because we work with vectors. You're adding to it 1 for the bias. Remember, so you make a 784 dimensional, 785 dimensional. You take its transpose, you multiply by the betas, and in the end, you do a -1 after you do argmax. Why this -1? Yeah, and this is where you show to your Python friends, and they tell you they never want to use Julia because Julia is kind of one-based indexing, right? But I mean, there's pluses and minuses, right? So digit 0, right? So you want to move, you want to say the digits 0 to 9. Okay. All right. So you've done that. This is your classifier. Let's use it. Let's do it. So let's do linear classify. Okay, so let's take the test data because we trained it. We didn't use a test data. Okay. Let's take test data 1 like this. This is like the first test image. Okay, here it is. I mean, we can do also a heat map of this if we want. Let's took our test. Okay, that's this, and let's do heat map of our test. I think our test transposed y flip equals true, label equals false, I think, just to make something, I'm not sure if that's needed. Okay, what is this one going to be? 7. Okay, let's just make sure. If we do test data 2 for the labels, 1, the first one, 7. Okay, I mean the test is okay. Let's do linear classify. That's our data, yeah, our data. Test data, our test. Sorry, our test. Our test is an exciting moment. Let's now do linear classify on this guy, because linear classify wants to get like a square thing. Okay, it doesn't want to get a vector. That's how we did it. I mean, it's not 100% accurate. Okay, don't do this. Oh, it's a 7. Okay, it worked. All right, that was it. It worked. So it worked. But if we do it for about 1 in 10 or 14 out of 100, it won't work. Okay, the accuracy here is going to be 86%. All right, so if you now add to this simple model, if you now add the following, if you go here, and after this happens, you add a nonlinearity. So you take this thing and you now stick it in something nonlinear, like a sigmoid function or a ReLU function or some tanh function. And then maybe you stick it again in another layer that does the same thing and add another nonlinearity and another layer, no, the same thing. That's a deep neural network. Okay, and with deep neural networks, you can get to 98, 99% accuracy on this data. Yeah, what's your question?
You say stick it in again. So instead of sticking in the X again, we would stick it in the
Yeah, you recursively apply this thing. I mean, that's more of a discussion, right? But basically what you would do is you would go and you'd mathematically, let's just see this quickly. So if you go to chapter 5, feed forward network 640. Okay, so you go here and you say, my function, this, so you guys are mathematicians, so a bit of notation is okay. All right. So my function here, this thing I'm highlighting, there's a lot of notation there, but that superscript square 1, etc. That theta 1 is like the first layer. And that's just a linear function, but also some nonlinearity. Okay. And on that, I then compose it with a second one. and a third one, and a fourth one, etc. Then this thing is called, and sometimes people draw it like this. You would have seen images like this because this is like a matrix multiplication and a nonlinearity, etc. This is called a feed-forward deep neural network. That can already get us great accuracy. Okay, and of course for images, you're also going to use something else called convolutional neural networks, but that's a whole nother story. That's not in this course. Do the deep learning course next year, Stat 3007. You'll enjoy it. That's all of that, but a lot of coding. Tell your lecturer to use Julia there. No, I'm joking. Okay, actually, I'm not joking, but no, do whatever you want, of course. Yeah.
So if we were to add another layer, what the things in the second layer, would they be the layers?
Each layer would have its parameters. So the parameters are now this kind of, so each one of the theta is like a beta, but you have many parameters. So each layer is a parameterized function. Okay, yeah, but that's not our discussion. We just don't have time for this. Not a deep learning course, but basically what I'm saying, you saw it work from first principles for this digit 7. Thank God that the first test image worked for us. Okay, and if we now run this code, so let's run this code here. So what I'm going to do in this code is I'm going to apply this function we created. This function is our model, okay? That's our model, linear classifier. We're going to apply it on all of the test images. How many elements are in this comprehension? How many test images? 60,000 train, 10,000 tests, right? We didn't use the test images for train. So I'm going to apply that. I'll get predictions. So I got now 60,000, I got 10,000 predictions. So if we do predictions, I got 10,000 predictions, okay? Yeah, or I can do, I hope this will work. I've got 10,000 predictions and we see they're kind of uniform, okay? So there's about zeros, ones, etc., up to nines, okay? Now, I can then do something called a confusion matrix. So a confusion matrix, let's look first of all at the output. The output, each row, the first row are the observations that were supposed to be zero, supposed to be predicted as zero. The column is what they were predicted as, right? The confusion matrix captures confusion, all right? How is confusion observed? Confusion is numbers in the off diagonal. Okay, we thought it was like these 18 values here, we thought they were what did we think they are here? 2, right? 0, 1, 2, but they're actually a 0, right? Where do we have most of the data? We have on the diagonal. How do we compute the accuracy? Well, the accuracy is just how many elements are on the diagonal compared to the rest, divided by the rest, okay? So 86% of the values are on the diagonal. Okay, that's the accuracy. Right, so that's the confusion matrix. We're doing it here manually. It's just a bit of basic Julia on how we're doing it. Okay. All right, so we've got a couple more questions. No, all right. So good. So this was what did we see in the story so far? We did supervised learning. We used something very simple. We just used least squares that you've used in different ways in different times, etc. Maybe you're not across all of the minor details of least squares, but it doesn't matter. And this thing kind of worked. Now, I told you on the way that the way you would typically do this is not like we use the smart mathematical pseudo-inverse, because for deep neural networks, or even the next thing I'm going to show quickly, you can't, we're going to leave in 5 minutes, okay, 6:50. I see people kind of ready to launch, but you feel free to go. Yeah, no stress, no stress. Oh, good. It's no chains. For the record, the people at home, somebody's now leaving. That's bus is a bus. All right. Funny, in the first 2 years, we ran it till 7. We squeezed every little moment. So we actually did a full, but everybody's been finishing at 6:50, right? Yes, we will do. Okay, we might have been a second before. So the So we did learning. I'm just going to show you just for a second where we're going tomorrow, and we'll spend the time on this tomorrow, and let's finish. I see everybody wants to go. Enough last week. So we did now learning, but the thing is we did the pseudo inverse. We didn't do gradient descent, right? The one learning step, if you go back to the code, was the thing where you really computed something was in this line, this pseudo inverse. Okay, this is where you did one computation because linear algebra told you what the minimum looks like. It's pseudo inverse times y. Now, if you go with a model that's slightly more complex, and we'll discuss this tomorrow, and the model is a model that now there's some typesetting issues, but basically it takes the same thing. So LaTeX kind of broke here when we filed. It takes the same thing, but it applies a nonlinearity on it. The nonlinearity is a sigmoid function. The sigmoid function is just a function that looks like this. Okay, we'll see it tomorrow. Right. Then what we're going to do is we're going to run gradient descent, and I'll just finish by running it for you, so you get a feel for what learning feels like, and then we'll understand this more in depth tomorrow. So copy this code, let it run. Sorry, this is complicated. So now what you're going to see here, you're going to see some logging, some printing. I think it's pre-compiling of how learning more feels like to the machine learning professional. So this thing has a loop where each time we're going to do gradient descent steps. Okay, you're going to compute the gradient here on this line, a gradient of the loss function. And then you're going to do a step in the gradient descent direction. So now my laptop is soon, if you would be near it, you'd hear the fan going. The laptop doesn't have you probably had that on your projects as well. So the laptop doesn't have a GPU, okay? It has, but Julia doesn't use the laptop's GPU here, all right? And it is each time running on the data. And from time to time, it's also checking the accuracy. So as you can see, we've run, and we're already by epoch 5. What have we done here? We already managed to do better than the linear model. Okay, and we'll get to this tomorrow. You need to do this if you do option task 2A. You need to do this, right? Which is what I think most of you would do in part 2 of the homework. All right, accuracy got to 89%, and this thing's learning. So let's discuss the details of this for the first half of tomorrow. And the second half, we'll speak about decision trees. Just any final questions, something? Yes? This is still one layer, but with a nonlinear function, and it's not doing, and this is just so you know what's running here. This is softmax regression, where the output is actually a 10-dimensional vector. It's not just one. So it's not doing this one versus rest. It's doing, it's kind of giving you a probability vector, and it's choosing the maximal probability as your output. We'll speak about the details tomorrow. All right, thanks for your attention, and peace. Bye. Questions at home? No.